And another thing, many of these scalable graph data management solutions tried, except one which is on the board, is that let's put, since we know graphs are really complicated beasts which have very diverse kind of relationships between them, and we also know that RAM is getting cheaper, let's assume that I can distribute this graph over many machines and each machine has GBs of RAM. So let me just put all the database in completely in memory when you need to actually perform transactions on them, right? So if you look at Neo4j, it loads the entire graph into memory when you first fire any one query. Until then, it's peacefully sitting on the disk. So your first query can easily take few hours. It loads everything into memory. And then after that, every query is like super fast. Zoop, 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 it comes through, right? So average query response times are extremely good, but the first cold start queries are pretty bad. But on the other hand, if you are trying to look at billion node graphs, Neo4j really struggles, even on fairly large servers that we have tried on. So the alternate solution is, let's put everything on disk and just do it super fast through some means. We don't know how, right? So there is one solution that RTF did, which is basically what most of my work depends on, is that essentially look at triples and look at what kind of access patterns that you have. So you can access using source and look for the predicate and object. You can look at predicate and look for source and object. You can look for object and predicate and source, right? So let's create multiple indexes which are storing the same redundant information in some sense, right? And just store it really compactly in a very compressed format, and then add some more indexes just to make life easier for few other queries which do not follow this kind of pattern.
That Blinks and all of that?
No, Blinks does everything in memory. Blinks, banks, everything.
No, it does index.
Even the index is in memory, right? So there the focus is on even computing the Steiner trees on memory is expensive. So you really want to speed that up. So they maintain these fringe nodes and try to do it very fast.
Even bigger index.
Exactly. But everything is in memory. It doesn't ever go into the database. I mean, on disk.
This yours is on the disk.
Yeah, it's not mine. I just use it. So RDF was done in Max Planck Institute, and it's perhaps the fastest RDF store I have ever seen so far. Okay, so that's why it's called Triple Express, right? And they have added transactional support. And what I'm working on is to add analytic support on top of RDF So they did transactional side, and we are adding analytics side, trying to do mining operations or even recursive reasoning kind of things.
Suppose we categorize the entire graph in the formal communities, distinct communities, and based on that, above that community, if says that as it is that like this kind of tables we use,
Yes.
then will it make fast?
It will surely make faster, all right? But again, things are so messy that constructing such communities is not as easy, that you are not as clean as you would see on social networks.
These strict communities will give you very high level of purity, and then it will reduce search time also, because
Yes.
it will load only community,
Yes.
and then related community,
Yes.
connected community.
Yes.
So basically, like a type level graph, high level.
Exactly.
Lifted to the type.
So you are basically trying to implicitly derive some types and trying to move it up the hierarchy.
Yes.
You can do that, but at least I have tried it on Yago and it fails quite miserably, because the communities turn out to be very small in size, and then you have really high type hierarchy, really deep type hierarchy, and each one has very little filtering.
Hierarchy means there will be community, and each community will contain some set of nodes, and there will be no hierarchy. Suppose first there will be some metadata which represents the community, the adjacent community, just like you use the one-way diagram
Yes.
to search the nearest hotel or like
Yeah.
reach the destination and search the nearest.
You can do that. You can do that. But I can assure you the performance will not be any better.
The
I can assure you
definition
this.
of community is not clear in
Yeah.
this kind of graphs.
I mean, you can run some community detection mining algorithms and try to just group them, but your queries will not be of that nature. So let's assume, again, go back to our good old The Expendables example. At some point, Bruce Willis and Dolph Lundgren were in two different communities. Dolph was always in martial arts and largely Europe setting, right? And he was not in the big hits like Bruce Willis was. So in any definition of your community structure, you would keep these two separately. And you added one node which connects these two. And your queries now are all about The Expendables. So every time you have to touch this community and that community, then your community is not really useful, right? So you can easily extrapolate it to even more complicated settings.
Basically, distance in a graph is extremely fragile concept.
Distance is,
It's
yeah,
very fragile. You add one edge, you're dead.
Because it's semantic distance. So
Yeah.
it depends really on the queries.
so we can discuss this further. I mean, if let me just proceed, and I can see that the time is way past. And then we will try, now that we have convinced ourselves that linked open data is actually a graph with some additional little details like labels and so on. Let's try to look at what are the standard graph problems and how they are related to linked open data setting. Okay, I mean, these are your, at least the things that are in the blue are your undergrad math, right? So you have reachability queries. You are given with two nodes. You want to find if these two are connected. Okay, so we have studied different solutions for it in graph algorithms courses. And then you actually have another which is not looking for connectivity alone, you are actually looking for how they are connected. Give me all the nodes that are in between, the shortest path between these two nodes. Clearly, if two nodes are reachable, the second shortest path can also be found. That's guaranteed, right? So these are in some sense answer somewhat the same setting, but just that shortest path is little more informative than reachability. And then you have totally arbitrary pattern queries, right? I can form any kind of pattern in my query template, which could have wildcards, which may not have wildcards, and then I want to find out all instances of this in the graph. So these are the three main graph problems we look at, and many other problems that you see can be decomposed into some variant of these or some group of these, right? PageRank, for example, you can look at it as some variant of computing many reachability and shortest path queries, right? Steiner trees, for example, well-known solution is to use shortest path trees. Okay, and if you link them back to Sparkle and RDF, you can see that reachability queries by themselves don't exist in Sparkle, all right? Except when you are looking at the extensions like property paths which are coming through, which says that, okay, if A can reach B, then pick that B as your bind variable and then start processing something underneath, looking for patterns. So one of the first examples I gave was find me all friends of or all connected nodes from Srikantha, right? This was one of the examples I gave. I could add additional constraint, additional structure on the query saying find all reachable nodes from Srikantha and return me only those nodes which have certain graph structure around them. Those who work in TCS and
Reachability not in Sparkle, can't you just say from A question mark X question mark Y and that's it?
no, you need also star. If you just have question mark X, it is still one edge.
Oh, no, but there's no star.
There is no star. Star is coming in the property paths. Same thing existed even in XML. So in the XPath and XQuery in the beginning, they did not have a star, but later they added this star. Stars are always painful. Okay. So since reachability is being added, clearly shortest path wouldn't have existed before, but now again people have realized shortest paths are required. So there is efforts for adding shortest paths as part of the Sparkle extensions. And pattern queries, almost all of Sparkle can be seen as a pattern query.